Hey guys, this is Mr. Sal. We're going to look at composite and inverse functions. Just a quick lesson on that, so thanks for watching. Don't forget to like, comment, and subscribe. In the real world, functions frequently occur in which some quantity depends on a variable that in turn depends on another variable. Functions like this are called composite functions. So something is going to be changing based on something that's related but very different. Maybe it's not so applicable to everyone, but for example, how much bacon you can eat would probably depend on how much cholesterol you have, right? Yeah, right. Something to that effect. So something like this, this is just the notation for it. It looks like fog, but that little dot there is just a function notation for composite functions. So it's really f of g. So we're going to figure out what f of x is based on what g of x is. That means that we have to start kind of like with order of operations, the parentheses there. We have to find out what g of x is first, and then we find whatever f of that is. Okay. So like in this example, it's f of x equals x minus 2, and then g of x is 5x, and we have that in different colors, so it kind of corresponds, right? Well, f of g of x is the same as, right, this right here is f of g of x. It's really said the same way, it's just written different right here, f of g of x. Well, g of x is 5x, so we're really figuring out what f of 5x is. And we're replacing the x with that blue 5x right there, so it's really 5x minus 2. Okay, I mean, let's say that this g of x right here, let's say that this g of x stuff, let's say that it equaled 10. Right there. Well, then you'd have f of 10, because that's what g of x is, right? We replace g of x with 10. And then we would replace the x in f of x with 10, and then you'd still have that minus 2. Alright, just so, we can see this again, right? Is this notation right here. I think it's better written like this, but a lot of math people prefer it written this way. The reason why I like this method is because it shows that we have to figure out what g of x is first, and then we figure out whatever f of x is based on that value. This is just the function machine stuff. So notice it's flowing this way. Not that anyone cares, but it's a really pretty picture. Right? You drop in x into the machine, and then it goes through the machine, and then it spits out whatever g of x is from that function, and then that goes into the f function machine, and then it spits out something, well, sometimes it's different, but it's something brand new. And we can see, not that you care, but we went from little sphere balls, whatever, and then we changed them into cones. All right, let's do each of these separately. All right, so let's start with f of g of 0. All right, so it's f of g of 0, so we're going to focus first on this g of 0 stuff right there. So don't worry about what f of x is yet. All right, figure out what g of 0 is. Well, g of 0, right, we'd have the 6 minus, but the x now is 0 squared. So, you can evaluate that. 0 squared is 0. 6 minus 0 is 6. So ultimately, if I were to rewrite this with the information we have now, it's really f of g of 0 is 6. Well, that's not too bad. We've seen that kind of stuff before, right? Because f of x is 9x minus 7. But now we're replacing the x with the 6 that we found from g of 0. So it's really 9 times 6 there. So f of 6 would be 9 times 6, which is 54 minus 7. 47 right there. So f of g of 0 is 47. Now let's do g of f of 0, okay? Well, once again, we're just going to focus on f of 0 first and figure out whatever that is. Okay, so it's f of x, which is 9x minus 7. But we know from this expression that it's f of 0, so we're just replacing the x with 0. Well, evaluating this one, 9 times 0 is 0. 0 minus 7 is negative 7. So now we've got g of, we'll do it like this, f of 0. But we know f of 0 is negative 7. So we're going to replace that with negative 7 here. And that was g of x, right? So it's 6 minus x squared. And we're going to be replacing the x squared with negative 7. Like this. Now you could plug that into the calculator. Just be careful with the way that you plug it in. So g of negative 7 equals 6 minus 49, which would be negative 43. And that is g of f of 0. And that's our second answer right there. All right, now we have a table of values from these. Again, we're just focusing on whatever's inside that big set of parentheses, like this first one, right, is g of 6. So let's figure out what g of 6 is. All right, so in the table, I'm looking for the x value that's 6, because it's usually g of x, right? But now it tells us that the x value is 6, so I'm looking at this one. Well, the middle column is f of x. What I really want is the g of x column. So I'm looking at that second column where x is 6 again, and that tells me that g of 6 is 8 from the g of x column. So g of 6 is 8. So this ends up being f of g of 6, which is 8. So I'm going to have to go back to the table on this one, and I've got to find where x now is 8, which is this row. But I do want the f of x column in this case. When x is 8, f of x is 1. So f of 8 would be 1, and that's actually the final answer for this f of g of x stuff, 1. All right. G of f of 5. So once again, we're kind of looking for f of 5 first. So I'm looking for the x value is 5. And f of x is this first, or this middle column right here. So f of 5 is 6. So this ends up being g of f of 5, but we know f of 5 is now 6. So now I go back to the table and find the x value that's 6, but I want the g value that corresponds with it, and that is 8. So g of 6 is 8. So g of f of 5 is 8. All right, so what do you guys think? Now this is f of 4. All right, so we're focusing again on f of 4. So just looking at that table, right, I've got my x value that's 4. What is the f of x value when x is 4? 5, right? So f of 4 is 5, which means that we're really looking for f of 5, because we replaced f of 4 with that value, 5. So what is the f of x value when x is 5? 6. There you go. And that would be the answer for that part. All right, take a moment and try that last one, g of 1. Let's look. Okay, g of 1 is 7, that value. So we're going now, right, because that g of 1 is 7. So now we're looking for g of 7. So we're looking at the 7 value now, and its corresponding g of x value is 1. Well, we're going to do the same thing, but now with graphs. Okay, so again, we know the x values are along these x-axis right here. And our y values now are f of x or g of x, depending on which one it wants us to figure out. Alright, so this first one, we got f of g of 4. So let's figure out what g of 4 is. G of 4. So that's an x value of 4 on the g of x graph, which is the second one. So I'm looking for this x value of 4. And its corresponding g of x value is 2. On that, right? Just looking at that 2 right there. So I'm looking, in actuality, for the whole thing, it'd be f of g of 4, but g of 4 is 2. So now I'm looking on the f of x graph, which is this one on the left, and I'm looking for the x value that is 2, which is right here. And its corresponding f of x value is 2. You could say corresponding y value. It's up to you guys. That's a 2 right there. So f of g of 4 is 2. Let's look at the next one. G of f of 3. Alright, so once again we're looking at f of 3. So we're looking on the f of x graph, which is the one on the left. And I want the x value that's 3, which is right here. And its corresponding y value is 0. So what we're really looking for is g of f of 3, but f of 3 now is 0. So g of 0, we're looking for that x value on the g of x graph of 0, which is on the y-axis. And it corresponds with g of x is 5 right there. So when x is 0, g of x is 5. That's our answer right there. Alright, you guys take a moment to try this next one. F of 0. Okay, so kind of looked at some equations now, then the tables, now we got the graphs. What do you guys got? I'm sorry, I just couldn't hear you, I guess. It's all the hair in front of my ears now. So, yeah, it's 4, right? Then try g of 2. Has anyone got it? 5. That's excellent. Alright, now we'll do more with these functions. But we're not given specific values to find. We're just going to be, I guess, plugging these into the other functions, just like we saw at the beginning there. And when we simplify these, we're just going to have another expression to deal with, okay? So this first one, find f of g of x. So I'm looking at f of x on this one, which is x squared minus 8x. But it says that we're looking for, in reality, it says we're looking for f of g of x, right? So I'm going to replace all my x's with g of x. And yeah, not everyone needs this step, right? But I'm going to replace now all of the g of x's with what it actually is, and that's x minus 2, right? Because I want the expression from that. Well, from here, we're just going to simplify this stuff. So I have f of x minus 2. And I've got that x minus 2 squared. And, you know, we could show the work over here if we wanted to, right? X minus 2 times x minus 2. Then we're going to x squared minus 2x plus 4. So it's really x squared minus 4x plus 4. And then we got this negative 8 that we should distribute into that parentheses. So negative 8x plus 16. From here, we're just looking to combine like terms. So f of x minus 2 is x squared. There's nothing else to combine there. Negative 4x's minus another 8x's would be negative 12x's. And then 4 plus 16 is 20. And that is f of g of x. All right, g of f of x. So g of x is x minus 2. But this is g of f of x. And f of x is this x squared minus 8x. That f of x now is now x squared minus 8x. And then we got that minus 2. Now if we look closely at this one, there's no terms that we can combine on this. So that's going to do it for us on this one. Next up is g of x. Well, this is g of x. And that's not too bad. But let's just look at g of x for now. But instead of x, right, we got that g of x stuff. And g of x is x minus 2. If it helps, you can put that in parentheses. Just be careful. It's a minus 2 in red, not negative 2 times that parentheses, all right? So no distribution necessary right there. So we've got g of x. And if I were to simplify this new expression, I'd get x. Negative 2 minus 2 is negative 4. All right, what about f of x? Well, let's look at what f of x actually is. That's x squared minus 8x. But we want f of x in that x stuff. And f of x is x squared minus 8x. Now this is that binomial squared now. And we've got to replace this other x with x squared minus 8x. So let's take a look at x squared minus 8x squared. We'll expand it. Alright, I'm going to skip a few steps just for time's sake. So x squared, and then we got minus, now that's, oh I'm sorry, that's to the fourth right there. Minus 8x cubed minus another 8x cubed plus 64x squared. That's a squared. And then we also get, just combining those like terms, I got x to the fourth minus 16x cubed plus the 64x squared. So that was this portion of it. Alright, then let's do the distribution of this negative 8. So that's negative 8x squared plus 64x. Okay, we got those x squareds that we can combine right there. And then nothing else really changed on that. And that is our simplified expression for f of x. The next type of problem is to figure out what one of the functions is given the composite function. So if f of g of x is x plus 6 to the power of 6, and f of x is x to the power of 6, then we can kind of see right here that this x, right, I mean, I don't know, maybe, I mean, you could use different letters on that, probably not y, just to kind of understand that, I don't know, w, right? Well, what did they replace x with in this case? I mean, we got that power of 6 right here. So really x just became this w minus 6 stuff right there. So g of x would have to be, I mean we use w, but whatever, x plus 6. I just trying to use the w's to kind of clarify that they kind of are different x's. They're x's but for different functions. So you can kind of use different letters for those. So it's f of g of x, all right? And we have this x plus 6 to the power of 6 in there. What we know is that f of x is actually x to the power of 6. So it should be f of g of x, though, which is really what we want right there, right? Now, let me use different colors. F of x was x squared, x to the power of 6, rather. But instead of x now, we've got this g of x stuff, right? Now what we do know is that the actual f of g of x, just from the top there, is x plus 6 all to the power of 6. So we can kind of see that g of x became this x plus 6 stuff. I don't know if that was a better explanation, but that kind of helps us understand, hopefully, that g of x is this x plus 6. Now, it's not to the power of 6. That's part of f of x. G of x is just this x plus 6 parentheses right here. All right, this one now is f of g of x, and we want to find f of x in this case. So we don't really know what f of x is. All right, f of x, we don't really know what it is yet, but we do know that f of g of x, so again, hopefully the colors will help with this part. We know that it's 1 over x minus 1. Now again, the objective here is to find f of x. And what we do know is that this g of x is x minus 1. So if I can just figure out where g of x is in f of g of x, then it should help us figure out what actual f of x is, right? And we can see that x minus 1 is that denominator right there, x minus 1. So that means that f of g of x is really equal to 1 over g of x. Now that means that red g of x in the denominator is where we replaced x for f of x, right? So that means that f of x would have to equal 1 over x. I guess that's kind of working backwards. We could go back the other direction just to make sure, right? So I would replace this x with the g of x, which is really x minus 1. Which is what it shows us in the beginning right there. This one has more words than is necessary. Well, that's okay. So we got this function d of p, which gives the number of items that will be demanded when the price is p. The production cost, c of x, is the cost of producing x items. How would you determine the cost of production when the price is $7 as a function, all right? So we know we're looking for c of x on this thing, right? Because it wants the cost. Okay, now we're not actually going to figure out what the value is. We're just going to write the composite function for this, all right? Now, the other thing that they gave us was the demand based on the price, and the price they're giving us is the $7, okay? So we're going to figure out what the cost is based on the demand, which means that the x is really the demand based on the $7 cost, or price rather. So I'm going to replace the x with the demand based on the $7. That's it. That's our answer right there. Let's just look at one-to-one functions, not worry about this inverse stuff. You can't really have an inverse function unless it's one-to-one, if I remember correctly. Not that it really matters right now. But we know, just going back, that a function is a function if for every x value you only have one corresponding y value. Now if we look, again, if we continue to look back, right, this was more for linear equations and expressions. If we were to test this, we would take that purple line right there. Let me see if I can move it. Oh, it's not. Hold on. Just for functions, we would, or we usually would make some kind of straight line right here. Let's see if this will work. And we would make a horizontal, vertical line rather. And then we would scan this thing. And if it ever touched that vertical line more than once, then it was not a function, right? So if we had a line that was maybe more like this green one, this one, then I would take my scanner here, I would start scanning that thing, and as soon as it touches it in more than one place, then I know that it's not a function, all right? However, that's just for functions. A one-to-one function first has to be a function, which is why it's important to look at that vertical line test. But it also has to, it's kind of like the inverse of the function. 1-to-1 means that for every y value, you only have one corresponding x value as well. Okay. What that really is the horizontal line test. Okay. So if I were just to look at the graph, I could have a line like this, and then I would be scanning this thing. Now if I looked at that green one, right, it kind of meets this horizontal line test, but the reason why it's not 1-to-1 is because it was never a function in the first place, because it did not meet the vertical line test. It's got to be both for it to be 1-to-1. So let's look at the red line then. If I scan this red line, I can see that it passes the vertical line test. And then if I scan it with this horizontal line, it also passes that test. So I could assume safely that that is a 1-to-1 function, that red line is right there. If we look at lists of numbers, right, it's the same idea. If I have to check the x's first, just to make sure it is actually a function. If it's not a function, it can't be 1-to-1. But if it passes the function part of it, then we've got to check the y values as well. So on this one, we're going to look at the x values. I got 1, 3, 5, and 6, and that's a pretty good sign because they never repeated to give us different values, different corresponding y values. So that's a pretty good start right there. So we know it's at least a function right now. Well, now I've got to go through the y values, and if none of them repeat, it's automatically 1-to-1 because it was already a function. Okay, I don't see any numbers that repeat. If they did repeat, it would have to spit out the same x value in order to be 1-to-1. If it spit out a different x value for the same y values, it would not be 1-to-1. This one, however, we did not have any repeating values, so we would say that this is a 1-to-1 function. Alright, so let's go through this one. Again, we should check to see that it is a function. So I'm looking at just my x values. Again, nothing repeats, so it can't spit out anything different, so it's at least a function. But then I check my y values. I got a 3. But then I got these two 7s, which is pretty important. I need to look at the corresponding x values with these y values. They are different, which means it's not 1-to-1. So this one is not a 1-to-1 function. All right, is this graph 1-to-1? Well, let's check check to see if it's a function. So I don't see that it doesn't touch this purple line in any two places. So it is at least a function. Well, we should also check a horizontal line test for 1-to-oneness. Oh, there we go. It's touching in 3 spots. Is it 1-to-1 then? No, it is not. All right, what about this one? So once again, let's test the vertical line test on this. So just scanning this thing, it only touches it once every place. So we'll move on to the horizontal line test and just scan this thing. Whoops, I did that the wrong way. And it never touched it more than once. So is this one a 1-to-1 function? Yes. All right, what do you guys think about this one? Very good. Is this a function though then? Yes, it is a function, but it is not 1-to-1. Inverse functions. So when we want to figure out what an inverse function is, all we do is we switch the x and y values in the function or the equation, and then we manipulate the equation for y. That may be better with an example. Like this one. Use algebra to find the inverse of this function. Alright, so if I were to rewrite this, I would have y equals x minus 10. And that's just the straight function for that, right? But to find what the inverse is, I'm just going to replace the x and the y values with each other. So I've got x equals y minus 10. Okay? But I don't want it to be x equals. I want it to be y equals. So what would I do to solve this thing? I would add 10 to both sides. And I would get x plus 10 equals y now, which is the inverse function for this. In fact, you can, that's not a power of -1. That's just one way to show that it's an inverse. You're going to see that quite often, that notation. It's also shown like this. It's the f of x inverse, and that's how that would be said right there. So the inverse of f of x now is x plus 10. Alright, find the inverse function of this stuff. So again, I'm going to write it as y equals 5x plus 2. And that would be the actual function. So the inverse would be where I switch the x and y. So now I've got x equals 5y plus 2. And I'm just going to solve for y now. So to do that, I would subtract 2 from both sides. So I got x minus 2 equals 5y all over 5. Well, sorry, divide both sides by 5. And then I've got y equals x minus 2 over 5. To write this formally, right, it'd be f inverse of x equals that x minus 2 over 5 stuff. That's a really good question, and with that y, if you put that inverse, I'm okay with that, right? In fact, I probably should have done that when I changed them back here. Like that. That didn't come out very good either. Yeah, it's a little better. Now, if we look back, just real quick with the inverse stuff, right? We're just replacing x and y values, so it's not too bad. These first two parts are actually just f of x, so not a big deal there, right? F of 0, so what's the y value when x is 0? Well, yeah, there's x is 0, and it's 1 right there, so 1. Not too bad. We've seen that before. Then we got y is 0, right? Right here, so what's, and they probably should have put that there, is what is x when f of x is 0? So that's the y value that's 0. That's going to be on the x-axis right there, and that's going to be 3, like that. Now this next part is the inverse, f inverse of 0, right? So that looks like x is 0 in this case. So what it's really asking is when y is 0, what is the x value? Because it's the inverse, right? Because right here, this is, all right, we would look at this as f inverse of x. But now the x is 0. But remember, the inverse replaces the x and y's. So it's really asking what the x value is when y is 0. And that's 3 right there, right? Notice it's the same point that's right there in purple, like we found before. So it's just like they switched, right? So instead of the 0 being here, now it's in where the x is. Okay. The f inverse of x is 0, so that would be like y is 0, but remember that's switched, so it's really what is the y value when x is 0? So in that case it would be 1. I'll use a different color there, 1. So it corresponds to this point as well, which is, well, it's inverted. Now I said it corresponds. It doesn't mean that that's where those points would be. It's just saying that's the point that it's corresponding with. Okay, it's like we've inverted that point. For example, like the red point right there would be 0, 1, right? Well, it's inverted point, which is now corresponding with this blue value, right? would be 1, 0. All we did is we switched the x and y values, which is what we do when we're solving the equations, which puts that actual point right there. All right, and that brings us to graphs of inverse functions. It's just the same example. I got that blue dotted line right there. That's because all inverted functions are just reflections across this line. So for example, if I took the point, let's take 6, 2, this point right here, right, which is at 6, 2. Its inverse, so I don't know, inverse of this value would be, right, we're just switching the x and y's, then it becomes 2, 6, right? So that's 2, 6. And not that we can tell that, but it kind of makes a 90-degree, it's straight across from each other with that line. It's called a line of reflection. It's just reflecting that red point onto that purple point right there. But it has to make a 90-degree angle, but that's a whole different story on that. That's going to be how that works. If we started with something, for example, up here at, let's do -9, 8, right? -9, 8. If we reflected this, right, its reflection, or its inverse, would then be at, we're going to switch those 8, -9. So 8, -9, down here. Just like that. And again, it creates that straight across, or reflected across, that blue dotted line. Which means it almost acts like an axis of symmetry, which we've seen before. So something like this, right? We got match the graph of f of x. Let's ignore that second part for now, that g of x stuff. Just look at f of x, okay? Which is 1x minus 1. Now, this is a linear equation because there's no exponent for the x, and it's not in any denominator. So it is a straight line. And we know that it's going to have a y-intercept of -1 with a slope of 1 on that, right? So maybe I should have circled it in green because that's the green line, right? Which we should know because it's the only line out there with a -1 y-intercept, okay? So that gives us something to work with, 0, -1. Now if we were to invert that, just that point alone, then it would give us the point, right, we're just switching those again, -1, 0, so that would be the f inverse point, -1, 0. There's only one line that goes through -1, 0, and that's the purple one right there. So this one would be purple. Well, that leaves us with those other two, and by the process of elimination, it's just black or red, right? So we got g of x is -2x plus 4, and so that has a y-intercept of 4 with the slope of -2, so we know it's sloping downward. Well, the black one is doing that, but it doesn't have that y-intercept of 0, 4 like the red one does. So g of x itself is red. I mean, again, by the process of elimination, we could say this is the black line. But just again, to confirm that, we could say, well, the inverse for 0, 4 would be 4, 0. And the black line goes through that point, 4, 0 right there. So, again, I think that's multiple choice on the homework, so you just choose whichever color it is. So we'll sketch this one. We'll do f of x itself in red there, and then we'll do the inverse, f inverse of x in purple. Okay, but we've got to figure out what that actual, well, I guess we don't necessarily need to figure out what that actual function is. This is linear, so it's not too bad. It has a y-intercept at 0, 2, so we can put that point right there, and then it has a slope of up 1 to the right 2 from that fraction. So I'm going to go up 1 to the right 2, up 1 to the right 2, and then it gives us all these other points. Alright, then we'll just connect these points. Now if we went through each of these points and inverted them, we would be fine, right? We wouldn't necessarily need the inverse function. But just as a quick reminder on how to find that inverse function, so this would have been y equals 1/2 x plus 2. So the inverse, we're just going to switch the x and the y around and then solve for y. So right here we're just going to subtract 2 from both sides and then multiply by 2. We'll show the work. Inverse function there. 2x minus 4. So yeah, that's going to work out better. So that gives us this y-intercept at 0, -4 with a slope of up 2 to the right 1. All right, and we just got to connect those.